So welcome to the Kafka Streams at Scale talk, avoiding common pitfalls. So I'm going to start by introducing myself. So I'm Mateo Rojas. I'm from Quito, Ecuador. If you ever plan to visit South America, I would totally suggest you go to Ecuador. A very nice place, actually. We have a lot of flora and fauna, so we are considered a mega diverse country. And we have a lot of chocolate and the Galapagos Island also, so you're welcome over there, and feel free to chat with me on LinkedIn if you want to go. So I've been working in the software industry for, I don't know, the last 7 years. A lot of them using Kafka for implementing communication between services, event-driven architectures and stuff like that. And some of other years using Kafka Streams, implementing namely an annuity platforms and a workflow orchestration engine. So I'm currently working at LittleHorse, where we're building the future of workflow engines. And you could say that, in a way, we are building the future of software development in that sense. That's my LinkedIn. If you want to go to Ecuador, feel free to leave a message. So the agenda for today. So the first thing that we're going to be talking about is what's LittleHorse. And you may be wondering why. And we need a little introduction into that because all the things that we're going to be talking about today, we learned because LittleHorse is implemented completely in Kafka Streams. So we're going to be going through that and the challenges that we faced, and it's kind of like how LittleHorse is using it. Then we're going to be going through an overview of the Kafka Streams, how Kafka Stream works and the configurations that we suggest you should use and how, making your app stable, and upcoming and recent Kafka Stream changes. Oh, and finally a Q&A for those of you who have questions. All right, so let's get started. So what's LittleHorse and how does it use Kafka Streams? So LittleHorse is a platform for developing workflow-driven applications. And what's a workflow-driven application, right? In other words, we can say that it's a platform for orchestrating processes in a reliable, scalable, and maintainable way. But let's dive into it a little bit so that we can understand what that means, right? Orchestrating a process in a reliable way. So nowadays, our applications have tremendous complexity. So long, hard days where everything could have been done within the boundaries of a single service, let's say a monolithic application or a single machine. Business processes requires a lot of interactions between multiple different teams, multiple different processes, external platforms, external APIs. So let's imagine this scenario over there where we have kind of this business process over there. So it's an order. Let's say that it's actually a process for putting an order, right? So we reserve the first thing that we do when we place an order is we reserve into the inventory. So that could be done into the database or on an API of one of our teams or whatever. And after that's done, we need to charge the credit card. Usually we don't have credit card engines to check the credit card. So we usually call an external API for that, let's say Stripe. And after that's done, and that process could fail too, right? And after that's done, we decide to ship the item. And by shipping the item, we have another team that does that. So we are talking about 3 different APIs at this point because usually multiple teams own this stuff. And at the end, we just notify the customer with an email. We can use SendGrid for that. And I'm going to ask a couple of questions here. So what happens if one of those calls fails? Like, what happens if shipping the item fails? How do I revert to the credit card transaction? How do I revert the inventory if those are in multiple different microservices? It starts to get a bit more complicated, right? We have heard about the choreography pattern for this, and the Saga pattern for this, but that implies a bunch of messages that different microservices will need to understand how to handle. So I will ask another question. What about retries? So, for instance, charging the credit card, what if Stripe is down? We need to implement retries, right? And that's simple. We have libraries for that. But we might need to implement retries on all our microservices, right? For all our microservices calls, which means that we either need to have something underneath like a service mesh that does for us, or a library that constrain us to use the same library and the same language across all our applications. So those are the things that we need to consider. So two more questions here. How do we do tracing? So if we want to trace a particular order and see where it went in all these different microservices, because there are different services, right? Owned by different teams with different logs and different traces. We need to start implementing a distributed tracing and logging mechanism. And we need to start using a trace ID so that we are able to see the flow of disorder across all our systems, which starts to get more complicated. And what about if retries, which we talk about retries, what about when they are exhausted? When they're exhausted, our application is left in an inconsistent state, right? Which means that we'll manually have to fix data, reconcile data, or we'll manually have to run other type of processes in order to do what the retry was supposed to do at that point. So I have introduced the problem, right? Hopefully. So that's where LittleHorse comes to the play and a workflow engine comes to the place. It's here to save the day in that way. So it allows us to build complex process orchestration with stuff that's out of the box so that you don't have to implement your retry logic across all your applications, for instance. So in this case, LittleHorse consists of a server. And bear with me, this server is completely built in Kafka Streams, 100%. We don't have any other dependency, which is kind of like the interesting part right here. And the LittleHorse server is in charge of receiving the workflow specification, which is basically the graph of operations that we wanna apply to the process. And you can see over there that we have got the workers. So in our example right here, we provide LittleHorse with the workflow specifications of what we want to do, which in this case is that. And LittleHorse will help us execute those tasks in the particular workers so that we can reliably finish executing that whole process, even if it fails. And it does the necessary retries, and we can also implement exception handling so that when shipping the item fails, we can quite easily revert the credit card transaction and remove the inventory reservation that we have, right? So basically, that's what LittleHorse is about. Well, why am I talking about LittleHorse in this presentation? It's because it's completely built in Kafka Streams, 100%. So no other dependency. And the way it's done is that everything in LittleHorse is a command. So we leverage Kafka. That allows us to leverage Kafka delivery guarantees, high availability, replication, and high throughput. So each command that we emit into LittleHorse, either to run a workflow, which is basically running a business process, right, is also stored into Kafka Streams state stores. We don't have any other database, just Kafka Streams state store. And if you're curious about how this all works, Colt is going to be giving a talk tomorrow at 5 p.m. about how LittleHorse is leveraging Kafka Streams. It's going to be quite interesting, actually. So, all right, let's deep dive into Kafka Stream itself. So an overview of how Kafka Stream works and what configurations we suggest we should be using. So what is Kafka Streams, right? I think that we all know this by this point, which is basically that it's a library for building applications whose input and output depends on Kafka events, right? I'm going to just add to that definition that the term real-time, right? Because it's a library for building real-time applications using the data streaming capabilities of the Kafka platform. But how does it do it? Sorry. So let's start from the beginning. So Kafka Stream provides us with the DSL, right? Or for more advanced user, it provides us with a lower level processor API that allow us to specify the things that we want to do or the processes we want to run with each event. These API allow us to build what we call topologies, which is basically just the graphs of operations that need to be performed to event. And there we go. We have one very big topology. And you might be wondering what the little boxes are. So let's start by analyzing this use case. So we have an input topic, very simple, right? We do some kind of filtering because we want to filter on whatever property. We want to do some mapping on some other object because that's the output requires another type of object. And we put that into the output topic. And then afterwards, some other processing over here, it's reading from the output topic, doing another mapping, and put it in the result topic. So the interesting thing right here, you may be wondering, why am I going to such a low-level detail? Because we all know this by now, but we'll get to the really interesting part. So the first thing that we need to understand about this graph is that the whole thing is a topology. But each independent standalone process right here is a pseudotopology. And how do we differentiate that? Is because everything that's happening within that pseudotopology is happening in the same process. So there is no network partition within them. And network partition means that there is no topic in between those. So they can be processed in the same thread. So this is a really simple topology, but Kafka is a distributed event log. And what means is, it means that topics usually have multiple partitions, otherwise they are useless, right? We cannot parallelize without multiple partitions. So in reality, a topology looks like this. Let's assume that our input topic has two inputs. Sorry, not two inputs, two partitions, 0 and 1. And we can see that right now, each subtopology is going to be parallelized into a task. So basically, a task is a way of parallelizing or executing in parallel each subtopology based on the partitions that we have for a topic. We can define it as the fundamental unit of work for a Kafka Stream application. But how these tasks are actually executed? Oh, and one very important thing right here is that you can see that the name of the task, right? This one is 0, 0. If you take a look at the subtopology, the first subtopology was subtopology 0, right? So over here, the name of the task is going to be the number of the subtopology and the number of the partition. So in that case, subtopology 0 partition 0, subtopology 0 partition 1. Now, how is this actually executed? Because we have seen the concepts, right? How is this actually executed in Kafka Streams? So Kafka Stream basically creates an stream thread to be able to run all these. Only one by default on the applications. If we want more than that, you can create more, but one is created by default. Each stream is in charge of, there is a bunch of details into what each stream does, so this is just a very high-level overview of what it does, but you will get the idea. So each stream thread has a single consumer that's going to be reading from all the topics that the task needs to consume from. It has got a single producer that's going to be producing all the events that the task needs to produce. And essentially, it's going to be executing all the tasks that it gets assigned in the rebalancing process. We can talk about that in a second. The important thing right here is that given that consumers and producers are really optimized for high throughput, we don't need a consumer and a producer per task. They can just use one, which is a really optimal way of using it. And the Kafka Stream thread is also in charge of reading. I mean, it reads from all the topics and it distributes the events to each partition based on what topic each partition is concerned about. But the thing right here is that we don't usually have a single Kafka Stream instance. This is just a single Kafka Stream thread with a single Kafka Stream instance, and that's not a real use case, right? I mean, we wouldn't be able to scale if that were the case. So we usually have multiple Kafka Stream instances and multiple threads. You can have multiple threads within one instance, but it would also be advisable to have multiple Kafka Stream instances so that you can have failover, and we'll talk about failover. But in this case, what happens? One thing that you will notice here is that now that we have two Kafka Stream instances, the tasks are distributed among them through the rebalancing process. So now this Kafka Stream instance right here is reading from partition 0 of the 2 topics, and this one is reading from partition 1 of the 2 topics. But the thing is that up until now, we have been just seeing this stateless application. This one doesn't save a state, which means that if I wanted to just get rid of this Kafka Stream instance right here and put a new one, nothing is going to change. I mean, it's just spinning up a new application. We don't have the state. We don't have anything to catch up with. It's just going to work. And so the fun part comes when we start thinking about stateful applications. 1 second. So the fun part comes when we start to think about stateful applications. And let's imagine this topology over here on the left, which is a very simple topology, right? We have an input topic, of course, we always do. We have a filter, which in this case, we can filter by whatever property. And let's say that we want to count based on how many messages of a type we have received, whatever type that is, right? We have 2 ways of doing that. The first way would be read all the messages every single time we want to have the count, which is not performant at all. I mean, it would work for a Hello World application, but that wouldn't scale at all. And the second part would be to use Kafka Stream stateful capabilities right here. So Kafka Streams is concerned about high throughput and low latency. So it provides us with RocksDB to be able to have stateful applications. What happens here is that RocksDB is a key store database. And how Kafka Stream works is that whenever we receive a message, we do whatever transformation we want. It puts it into RocksDB. It puts also the state into the changelog topic, which is for resiliency purposes, so that if we want to rebuild the state, we just rebuild it from the changelog topic by rereading it. And then it commits a Kafka transaction if you happen to be using exactly one semantics. So one thing is that one really interesting thing is that we have talked about Kafka Stream being a system that have multiple partitions so that we can parallelize stuff. How does it look like in a stateful application? Quite easy. So it looks like this. So every single instance of the Kafka Stream application will have its own RocksDB, which is embedded, of course. And not only that, but given that the input that partitions have different data on them, this instance right here will have its data, while this instance right here will have its own data too, which is different data. But what happens, you may be wondering, what happens if we restart one of these instances, right? Like literally, I mean, because we have a container orchestrator like Kubernetes. Kubernetes decides to restart the instance, and what do? So the first thing that we are going to be talking about is using persistent volumes. And this might seem a little bit obvious, right? Like, but we're going to talk about it anyway because persistent volumes is a way in which we can, at least in a container orchestrator like Kubernetes, make sure that we save the state between restarts so that when we restart our Kafka application, it doesn't have to restart all the state into its embedded RocksDB data store. In Kubernetes, it's usually implemented using persistent volume claims and stateful sets. But yeah, this is kind of like the first learning that we have got. And if you're running Kafka applications, Kafka Streams applications on your cloud, make sure to always use persistent volumes, whatever that is for your orchestrator of choice. But now, using persistent volumes would solve the fact that our applications can fail. And our pod can be in an inconsistent state, or our application can be crashed, not necessarily restarted. So what happens there? Like, our application is crashed, instance B is still running. Kafka would try to, given that our application crashed, the Kafka rebalancing processing would try to move the task that we had right here, the task 0, would try to move the task to the instance B, right? That would be the most logical thing to do. The thing is that keep in mind that these are stateful applications. And if you happen to have a lot of state, the state from task 0 doesn't live on instance B. So in order to move it, you would need to restore the whole state. And that could take a lot of time if you have terabytes of data. So the other thing that we can consider when running Kafka Stream applications is standby replicas to the rescue. And a standby replica is just a way of replicating the state of the task into another app instance. So if we take a look at this, we have our instance A, which is completely running right now with task 0. It's outputting the state to the changelog topic and saving it to its RocksDB. And then we have instance B of the application. But one interesting thing right here is that now you will see that we have a restore consumer. And then restore consumer is reading from the changelog topic that was being outputted by the task 0 right here. And then restore consumer is going to be it's going to be filling the RocksDB over here on the instance B. And that's what we call a standby task. So if this instance were to fail, Kafka rebalancing process can just start pointing to instance B. And that way it would be almost ready to go. I mean, it would have a little lag, like minimal lag, but it would take us like 5 seconds to recover from that lag, whereas refilling the whole state. So how to properly use standby replicas? So the first thing that we need to consider is that they are disabled by default, so the default is 0. So if you're trying to run Kafka Streams on your applications and you have statefulness, I would suggest you start considering putting it at least 1. But the thing is that there are drawbacks to that, right? So one of the drawbacks is that you will have your state replicated on all nodes. Let's say, so that means that you would have double the size of storage, or you will use double the size of storage. Also, this will increase network utilization because multiple nodes will be reading from those changelog topics and restoring the state from those changelog topics, so that will increase the costs, something that you need to consider. But this does reduces the time to recover, so we need to balance those two considerations. One other thing is that you need to provision, if you plan on having 1 standby replica per task, you need to provision n+1 Kafka Stream instances, which means that if you have 1 standby replica configured, you need to have 2 Kafka Stream instances. I mean, otherwise it wouldn't make sense. It wouldn't have anywhere to replicate. And another thing that you can try doing is increase the restore consuming max poll records. So you can see over here that there are 2 different consumers. So the main consumer, which is the one consuming for events for the actual task, and then the restore consuming, which is consuming for just restoring for the standby task. And if you set a larger max poll records for that restore consumer, you can allow it to process data much faster. And that's kind of like a trick. So, all right. So after you have enabled standbys, your cluster and topology would look something like this, which is basically instance A, in this case, is running actively the task on ring 0.1 and 0.2, while it has a standby of 1.0, and instance B has those standbys on active. By the way, which task is a standby and an active where is controlled by the rebalancing mechanism of Kafka Stream itself. So let's say we have a way of recovering from failures, right? But let's say that we need to scale, because applications do need to scale on peak hours nowadays, right? So what do? So we could just create a brand new instance right here. And we can let Kafka Stream notice that there is a new instance and move the task. But again, the same problem arises, right? I mean, this instance doesn't have the state that the previous instance had, so it would need to restore that, and we wouldn't be able to, if Kafka Stream were to move that task and activate it on this new instance right here, it wouldn't be processing anything until it catches up with all the state restoration that it needs to do. And this is where warm-up replicas comes to the rescue. So warm-up replicas are just a mechanism or a special type of a standby task that Kafka Streams schedule on a node so that it starts catching up with the data and the state before it put it as active. So when Kafka Stream rebalancing processes decide that a task should be moved to a new node, it will spin up a warm-up, let it catch up until the maximum lag, and then it will move and activate it. So now it looks like this. So now it looks like this. When you spin up the new instance, you would have a warm-up there, which will be catching up until it reaches the configure lag that you have allowed, and then it will activate it. And then you can, it will be removed from there. But there are some considerations that we need to configure when we use warm-up replicas. So by default, the maximum warm-up replicas is 2. And this means for the whole application. And we have to take this with a grain of salt because this is different from the standby number that we put. So in the standby number, we put the number of replicas that we wanted each task to have. But over here is for the whole application. So let's say that we have task. Let's say that we have 5 tasks, right? And Kafka Stream wants to move 3 of them, and that we have max warm-up replicas of 2. What's going to happen is that Kafka Stream is not going to be able to put 3 warm-up replicas. It's only going to be putting 2. So you need to take that into consideration. The last one is going to have to wait because it wanted to move 3. Another important configuration here is acceptable recovery lag, which by default is 1,000. And what does it mean? It means what's acceptable for the rebalancing protocol or mechanism. What amount of lag is acceptable for the rebalancing mechanism to move a task to active? So if a warm-up replica still have like a lag of 3,000 and this is 1,000, it's not going to move it until it reaches there. If you cannot afford to have downtime on your application, then you would need to configure this to a lower number so that it doesn't move it. The lower the number, the lower the time you need to wait for it to become completely active. And one really important thing about warm-up replicas is that the way it works is that it do proving rebalances. So the only way for Kafka Streams to know and to move stuff around is on rebalances. There is no other way for doing. So in the case of warm-ups, what it's going to do is every 10 minutes or whatever the time is configured here, which is by default 10 minutes, it's going to be doing proving rebalances to see if the warm-up instances are already caught up to be able to move them, which means that you will have to wait at least 10 minutes, even if the warm-up replica was already caught up, to move the application or the active task. Sorry. So let's talk about a bit more of tips and tricks of making our application a bit more stable. So some of the little learnings, we talk about some of the learnings throughout the overview, but these are some little ones right here. So whenever you have your Kafka application and all the logic you put on your Kafka application, make sure to make it quick and fast. And if you're not going to make it quick and fast, you'll have to keep an eye on these 2 configurations right here. What's going to happen? So let's say that why is it important for a Kafka Stream application process to be fast? Let's take this example right here. So if each process takes like 100 milliseconds, right? And we have 10 events to process, it means that it's going to take a total of 1 second to process those events. Now, let's imagine at the scale that we usually run Kafka, which is millions of events, we are never going to finish, let alone replaying events. But if you ultimately want your processes to take a bit more time, let's say 500 milliseconds or whatever, because they are making an API call, you usually need to keep an eye on these configurations right here. So max fault interval milliseconds and transaction timeout in milliseconds. And why is that? Because if your process exceed those timeouts, you're going to get kicked out of the rebalancing group, and you're going to be triggering a rebalancing. So you could literally be causing yourself a rebalancing storm if your processes take longer than these two. The transaction timeout milliseconds only apply if you are using exactly one semantics. Other little tweaks right here. So make sure to always set up the appropriate session timeout. And what does the session timeout do? So we know that Kafka Stream has a heartbeat thread. Aside from the threads from the string thread that we saw, we have a heartbeat thread. And this heartbeat thread is sending heartbeats to the consumer group controller every now and then. And when it stops for whatever reason, either network failure or the application fails or whatever, then the consumer group coordinator is going to kick it out of the group when this session timeout kicks in. So let's say that you have an application and you have 5 instances of that application and you want to do a rolling restart, but your application takes like 5 minutes to start. And this session timeout is 1 minute. So what's going to happen is that you're going to get kicked out of the group over and over and over again. So you should at least make sure that this session timeout follows your application startup time. Although there are drawbacks to that, right? If you set a session timeout that is too big, what's going to happen is that if you happen to have an application that is actually failing, you are not going to know until that time runs up. So keep in mind that. And last but not least, exception handling. And this is a tricky one. So there are 3 points in which a Kafka application can fail. When on the consumer, there could be network failure or deserialization failures. On the processing, on the actual task, and on the producer, again, network failure or deserialization failures, right? So for the network failures, Kafka Streams already have a bunch of sensible defaults set up to manage that, so we are not going to care about that right now, but we do suggest that you set appropriate deserialization exception handlers for your consumer and production exception handlers for your producer, so that you either fail the whole application or continue, or when you have a record that's poison. I mean, but you get to decide that on what the standard for your business logic is, right? On how critical your operation is. You might wanna fail the whole application, in which case you would return a fail. But the really interesting one right here is the processing one. So there is a keep for this one that we are going to be talking in a second. But every single uncut exception over here in your processing or across the whole Kafka Stream application is going to shut down the application itself. And that can be dangerous. Why is it dangerous? So if you're using exactly one semantics and you have a stateful application and your application crashes and fails to commit an offset, fails to commit a transaction, sorry, what's going to happen is that Kafka Stream is going to consider that state to be corrupted. And it's going to throw that state and it's going to try to rebuild the whole state. So if you have a 1 terabyte application, that's something to worry about because rebuilding state is going to take a lot of time. So make sure to never throw uncut exceptions within your processes. And if you do throw exceptions, there is this stream uncut exception handler that you can implement to decide what to do and if an uncut exception is thrown, and to decide to gracefully shut down the application. So there are 3 ways to doing that. The first one is shut down this thread or the thread that thrown through the error. The second one is to shut down the application instance itself. And the third one is to shut down the whole application. So it's going to use the rebalancing protocol mechanism to tell other instances of Kafka Stream to shut down completely. So you're going to be shutting down your whole application. I mean, you get to decide based on your business constraints. And just one last thing over here is Rebalances on stateful applications are difficult. There are ways around it. There are ways to configure it, but try to avoid them as much as possible. So configure properly your applications. Sorry. And last, upcoming and recent stream changes. So we're going to be going through some interesting keeps and issues to keep an eye on for your Kafka Stream applications. So the state updater, and this is a new one and a really interesting one. So the way that Kafka Stream works right now is that a stream thread has got both the consumer and the restore consumer, and we talked about the restore consumer a few slides ago, right? But the thing is that it's a single thread, so it can either consume and process a task, or it can either consume and restore the state on the data store. It cannot do both. So if you're restoring a state on the data store, you're not going to be consuming for other tasks, and that's a problem when you have like 5 of these tasks and just one restore task assigned into a single thread. So the state updater that was recently introduced in the latest versions of Kafka Streams allow us to have a separate thread for restoring the state. So yeah, I mean, I would suggest to update your Kafka Streams applications if you have one running. So the next one is transactional semantics for data store. And this is kind of an interesting one. So remember that we talked about that in exactly one semantics, whenever a Kafka transaction fails to commit, it marks the state corrupted, which means that it's going to delete the state and restore the whole thingy. So now, from this skip, there is going to be this new configuration, which is enable transactional state store. That's going to allow us to disable that behavior. But it's not all perfect, right? There is going to be drawbacks of disabling that behavior. So the way the behavior currently works is that it saves into RocksDB, and as soon as it saves into RocksDB, you're able to query that data right away. And if the transaction fails, then the restore thingy and the corruption thingy. But if you disable with this new feature, what's going to happen is that it's not going to commit the changes into RocksDB until the Kafka transaction is completely committed, which means that you're not going to be able to query your state right away. You will have to query your state after the commit transaction interval configuration. Something to consider in your applications. And finally, exception handling during processes. So remember that a few slides ago we talked about this, that uncut exceptions bubble up and shut down the application. The thing is that there is a new keep that has been accepted, not implemented yet. That's going to allow us to implement an interface so that you decide what to do with those records, either fail the whole application or continue processing and just skip that record. So this is still not implemented, but I would suggest everybody starts using it once it gets implemented. So I think that's all I have.